Okay. Uh, so in the last hour, we proved the following. Interior of any set is open. Well, if interior is open, then exterior is also open because exterior is the interior of some other set. Uh, then, since uh, interior of any set is open, uh, the exterior of any set is open, right? Because exterior, because for any subset A of X, what is exterior of A? Well, this is by definition interior of X minus A, but interior of anything is open, therefore this is open. Okay. Also, by definition, right? Moreover, we have the following. Moreover, interior of A is by definition is in A, right? And thus, exterior of A, which is just the interior of X minus A, and this should be a subset of X minus A. Therefore, interior is in A, exterior is in X minus A. In particular, this set has no intersection, right? Interior A, intersection exterior of A is inside where? This is inside A and this is inside X minus A. So this intersection lies in this intersection, but the latter one is just the empty set. Therefore, interior and exterior never intersects. Okay, that's of course something reasonable. We define a third subset related to A, and it is the following boundary of A. Okay. The boundary of A for any set subset A of A of X. The boundary of A is defined to be the subset şöyle tanımlanıyor. Definition boundary of A X minus I take out interior and exterior from A. Whatever is left is defined to be the boundary of A. And from this definition, we immediately see that, first of all, these three sets are all disjoint, right? Because these are already disjoint, and boundary A is just defined the complement of the union of these two. So the first observation is that clearly, then clearly interior A, exterior A, and boundary A are all disjoint. Right? These are disjoint subsets. disjoint. And what else? Well, we showed that interior is open. Exterior is another interior that's also open. Union of two open sets is open. And boundary is the complement of this open set. Therefore, boundary of A is closed. Is always closed because its complement is open. Okay. Uh, do you have any questions so far? We defined interior. We showed that it's an open set. And then we defined exterior as the interior of its complement. Uh, Again, it's an open set since it is an interior. And finally, we defined the boundary of A as the complement of the union of the interior and exterior. And since these two sets, interior and exterior, are open, boundary A becomes closed. In particular, we have the following. In particular, uh, okay, hence we can write X as the disjoint union. Uh, Interior of A, right? Exterior of A and boundary of A. Because boundary is defined to be X minus this 2, therefore this is a disjoint union. Any two of these has no intersection, and the first two are open always, and the last one is always closed. So whenever you give me a subset of X, I can write X as a disjoint union like this, okay, for any subset A. Okay, let's see some examples. Uh, for example, let's see, let's consider R and with the absolute value metric. Let's see, for example, this set A to be 0 and 1. So it's open from 0 and closed from 1. Maybe I put also 5 here. Okay, what are the interior points of A? So here is 0, 1, and 5. Okay, maybe I, okay. So this point is included, this point is not. Maybe I should like this. Okay. And this point is included. Now, what are the interior points of A? Interior points of A. Efendim? 0, 1, open interval. right? Okay, yeah, very nice. If you choose any point here, right? Let's see. If you choose any point here, then clearly I can draw a ball around X that lies inside A. I cannot do this for clearly the point 1 because if you do that, then half the interval will be outside A. And again, I cannot do it for this point because whenever you draw an interval about 5, some points will be outside A. Therefore, interior is just this. What about the exterior? Well, exterior of A. So this is the interior of what? R minus A, right? Interior of R minus A. And what is this? This is the interior of, if I subtract A from R, I get what? First of all, I get everything except, starting from minus infinity to everything up to 0, including 0. And then 1 to 5. 1 is not here, 5 is not here. And then 5 to infinity. All right, the interior of this gadget. Well, this is already open, right? So, okay, let's see. So, minus infinity to 0. And then I have 1 to 5. And 5 to infinity. Okay, so here, this one and this one. Uh, this point, of course, excluded. Maybe I should write it this way. Okay. So what are the interior points of this? Uh, everything up to 0, excluding 0, right? In the interior. And then everything between 5 and 1 and 5. And everything after 5. Right? Interior of this is equal to this gadget. This was the interior. This is the exterior. What about the boundary of A? It was R minus interior union exterior. Okay. Well, you see, 0 is not here and is not here. So 0 should be in the boundary. Similarly, 1 is not here and 1 is not here. So 1 should be here. And 5. 5 is not here and 5 is not here. So boundary consists of 3 points. 0, 1, and 5. Okay. This is open, this is open, and this is closed. It's a finite set, it is closed, we know that. Interior is an open interval. Exterior is union of open intervals, right? These are all open. Uh, maybe before I continue, let me tell you a remark. We showed that interior is an open set, right? And indeed, uh, if you have an open set, then it's equal to its interior, right? Uh, so let me this way. If A is open, then for any x in x in A, there is some epsilon, right? Epsilon, sorry, epsilon positive, so that this ball Bx epsilon lies in A. But this means what? This is because A is open, right? Open means any point, for any point, there is some ball like this. But this means X is an interior point. Hence, X is in interior of A. So what we see is then any point in A is in interior. Hence, so that A lies interior of A. But interior A is always A. And this implies what? So that, okay, I already said A is equal to interior A. So if A is an open set, then it's equal to its interior. All right. Therefore, this gives actually a characterization for open sets. A set is open if and only if it's equal to its interior. Right. In particular, we see that a subset A is open if and only if and only if A is equal to interior of A. Okay. If they are equal, of course, A is open because interior of anything is open. And if A is open, then we have seen that they are equal. So we proved this. Also, you see, uh, uh, by the uh, definition of interior point, actually, moreover, uh, for any set A, interior of A is the largest open subset of A, and exterior A is the largest open subset of X minus A. The second statement is just the restatement of the first one actually for X minus A, right? Because exterior of A is just interior of X minus A. So the important statement is this. Interior of a set is the largest open subset of A. Okay, it is the largest open subset contained in A. And why is that? Well, that's because of the following. Interior A, remember, this was the union of balls like this, epsilon x balls, x is in A, right? Uh, I have Okay, X is in interior of A. Every point in the interior contains a ball that lies inside A. Right? Each ball lies inside A, and interior is the union of all such sets uh, balls. Therefore, interior is the largest open subset of A contained in A. And exterior is the largest open subset of X contained in X minus A. Okay, let's continue our examples. I inserted this remark, but let's now continue examples. Let's consider the discrete metric space. So, okay, let xt be a discrete metric space. X could be any set, okay? It can be a finite set, it can be the set of integers, real numbers, rationals, whatever you want. I consider it with the discrete metric D. Now, let A be any subset, then we know that A is open, then A is open, and thus, if it is open, then it's equal to its interior. Right? A is just interior of A. What about exterior? Similarly, exterior of A is just interior of X minus A, but interior of any set is the set itself because any set is open. So, in a discrete metric space, interior is A, interior of A is A, exterior of A is just X minus A. What about the boundary? Well, nothing is left for the boundary, right? Interior and exterior covers everything. It covers A and X minus A, and there is nothing left for a boundary. In particular, boundary of A, which is X minus interior A union exterior A, but this is X minus A union X minus A. Well, this is X minus X, and that's the empty set. So, in a discrete metric space, all boundaries are empty. Okay. So you see, discrete metric spaces are really, weird objects. They do not like anything we have seen so far. Example 3. Let's consider the set of integers in the metric space R with the absolute value. Okay. What about the interior points of integers? Well, so they are this point 0, 1, 2, right? N and -1, -2, and so on. Is there any interior point? Well, any ball around any integer will not uh, be contained in this set of integers, because any ball, right? If you draw a ball, this ball will certainly contains points outside integers. Therefore, no point of integers is an interior point. In particular, interior of Z is the empty set. Uh, R minus Z is what? This is just the union of intervals n plus 1 and from minus infinity to plus infinity, right? So R minus Z is a union of open intervals. In particular, it is open, which is open. Well, since this is an open set, its interior is itself. So exterior of R minus Z, which is interior of, no, I'm sorry, interior of Z, which is, sorry, exterior of Z, which is the interior of R minus Z, and this is R minus Z because it is open, since it is open. So interior is 0, exterior is R minus Z. What about the boundary points then? Okay, boundary points of Z. This is R minus interior of Z union exterior of Z. All right. So this is empty. This is R minus Z. So I have R minus Z. Well, this is just Z. So the boundary points of the set of integers is the set of integers. Okay, in this case, we get something weird. And maybe one more example. Let me see how many minutes do I have. Well, I don't have actually many minutes. So let me just write this. So let A to be the set of rational numbers inside R with the absolute value metric. So let me leave this as an exercise. Compute interior int a, ext a, and boundary a. Okay. Next time I'll talk about this, but till that time, think about this. What is the interior points, what are the exterior points, and what are the boundary points, and then we will discuss it on Thursday morning. Okay, let me stop here.